Hi everybody, welcome to Module 4. To have a solid understanding of measurement, you need to have a solid understanding of the principles of statistical analysis. This is an incredibly deep topic, so we're going to really focus on the areas that are the most important as well as the most common in advertising experiments. This is the basis for the majority of common measurement tools, so you'll see this a lot. Understanding this will apply to many measurement solutions out in the industry. So let's review these two scenarios. Please read both of these very quickly. All right, in scenario one, we have a beverage brand. Let's say it's Pepsi. They reach out to people who buy Pepsi. Then they see a lot of people who buy Pepsi after they see the ad. In scenario two, we have a smaller brand. They really pick up their ad spend, but almost no one who sees the ad buys the product, but all of a sudden they triple their sales. So who did better? To ask this a different way, which ad worked? With this information, it's really difficult to tell because in both these scenarios, we are looking at correlated measurement. First the ads, then the sales. Correlation as a statistical practice gets a fairly bad rap. Correlation is not causation and all that. And while that statement is absolutely true, it doesn't mean that correlated measurement is good for nothing. But it does mean that we need to make sure that we are using it the right way. Correlated measurement is ideal for understanding where your buying audience is. Do they play mobile games? Do they watch connected TV? Are they in families with kids? Do they purchase luxury products? Do they prefer video or display creatives? Here's a common method that many platforms will use in a nearly identical way. You always need to be concerned about data quality, of course, but the math is typically the same. Correlation lets you know something about your buyers and something about your buyers' behaviors, and that's very valuable indeed. But what correlation will not tell you is if people bought more because of the ads. Now, causal measurement, this is more focused on learning about advertising strategies and their effect on buying behavior. In other words, did they buy more of the product than they otherwise would have because of the ads? That's what we're trying to assert. The experimentation and more advanced causal inference methods are typically the path to this. Test versus control, sometimes called randomized control trials, sometimes A/B testing. This is the common language here. It's important to understand that if your tools are drawing causal insights or correlated insights, if you use one and treat it like the other, you will arrive at the wrong conclusion, and then you'll make actions that aren't actually aligned with the data. Interpretation is very important here. Causal solutions are where the statistical analysis really comes in, so that's where we're going to focus today. If we do cover more on correlation versus causation in our session next week. When we get into causation, we're the very first thing that we need to do is design an experiment. So let's walk through some of these steps. The first thing we need to do when testing ad effectiveness is establish what we think will happen. In advertising, this is pretty easy. We typically think that an ad will drive a positive result in some action or behavior. This is often sales, but it can really be anything. Page visits, searches, email signups, store locator pages, positive survey responses, store visits, item in a cart, nearly anything that you'd expect ads to do, provided that you have the conversion data in order to be able to measure it. From a reading, we see this example of children watching TV. We'll stick with that, but I'm also going to throw in an ads example so you can see how this applies and changes based on the scenario. In either case, we're going to begin with our null hypothesis. So here's the thing that's true about the population. They watch 3 hours of TV, or people buy what they buy. These are things in a null hypothesis. We now build our alternative hypothesis, which is a contradiction to the null. People don't watch 3 hours of TV. Ads will increase sales. So the alternative hypothesis is the bit that needs proving. This is where the burden of proof relies, and so all of this experimentation is to accept the alternative hypothesis and reject the null hypothesis. So we set out to prove this. This is where the actual experiment comes in. So if you see the third box here on the diagram, first we research to understand, we construct our hypotheses, we then experiment, we then repeat it many times. Iterative learning is important here. We analyze and report. So on the experiment step, in the advertising context, here are the things that you should really think through. First, that we choose a measured effect. The metric that where we want to observe the change. We then create a test and control population. We administer the treatment or the ad to the test population. We then analyze the effect on the KPI for both of the groups. So for some additional detail, in ads, we typically talk about KPIs or key performance indicators. Sales is common, but once again, this can really be anything. The KPI you care about usually determines the measurement tools that are available in your industry. There's only a handful of consumer packaged goods data providers, for example. Make sure that you change the campaign objectives to align with your KPI. So for example, in a buy one, get one creative, you may consider a survey that shows unaided awareness of the brand, though sales at the register feels like the better fit for that type of objective. Next, you're going to create your test and control population. There's a few ways to do this, but randomized control trial or RCT is considered to be the gold standard in the industry. In this method, you're going to randomly decide on a holdback population or a holdback group who won't receive the ad, and you're going to do this before the campaign begins. This is the most rigorous test. You'd be looking at a 50-50 split, but that's typically not totally necessary to have a valid and fully powered test. In some cases, you might see a 10% holdback, and in some cases, maybe even less. This is easy to think about from the context of a catalog perspective, right? Your holdback group does not get a catalog put in the mail for them. Your test group does get a catalog put in the mail for them. You want a valid test, but really you want everyone to get the catalog. You want to get whatever sales that's going to drive by shipping them the catalog. But through the experimentation, you need a valid control population who doesn't receive it. You want to keep that control population as small as possible, but still have a valid test. All right, some important notes as we are going through this. You always need to keep an eye out for control contamination. So this is when your control population, in fact, receives the ad. When you accidentally ship them the catalog, you now have a contaminated control. It's important that this doesn't occur. This can very quickly ruin test results, so it's something to be aware of. And then please note the process diagram here. I want to bring this up a couple of times, but you need to experiment and then you need to repeat. No matter what the results, you need iterations. You need increased sample size. You need a body of evidence to prove what is working. A sample size of 1 isn't going to be sufficient. All right, so we've run our experiment, we've applied our treatment. Let's get to the analysis. But sorry, before we can actually do that, we need to talk about statistical significance because it is vital to the analysis and can be commonly misunderstood. So, using our TV watching example. So, what if I said that children don't watch 3 hours of TV per week? I said they watch 2.96 hours of TV per week. Maybe you roll your eyes just a little at that. Is this actually different? Isn't that just noise or even rounding error? And this is where statistical significance comes in. It considers your sample size, the variance of your population, and its difference from the mean. It can help you say whether your results are randomly different or if they are non-randomly different, which is a really important distinction. All right, a couple of terms that may help you with this. So there's not going to be any testing on this, and I'm going to cover this rather quickly, and we'll definitely spend more time in the session on this week also, but it's very important to walk through a couple of these things for a basic understanding. Significance. So this is denoted by alpha in stats. It's 0.1 is common for the industry, and really it's the measure of false positives. The other term to think through is confidence, and this is the inverse of alpha. You can see this on the table here on the bottom right. 1 minus your alpha would be your confidence or significance level. So a 0.1 is a 90% confidence, a 0.2 would be 80%, and so on. So try to think of statistical significance as a confidence, less so than a probability. A confidence that the difference is not due to randomness. It's due to something other than randomness in the data that we have collected. So with an alpha of 0.1 and a statistically significant result, we can say that we are 90% confident that this is a non-random difference between the test and control population. Other things to be aware of with statistical significance, because they do seem to come up a lot. Sample size and alpha have a direct but non-linear relationship. So if you want to increase your confidence levels, you need a lot more sample size. There's also beta, which is false negatives. It's important to know that those reads exist. We just don't talk about them quite as much. Note that, and I do want to note this just as a personal note because I see this happen all the time, but the term statistical significance or stat sig is commonly misused. Is this a stat sig sample size? Does this query have statistical significance? And I think it's typically meant as accuracy and not related to a specific experiment, but it does come up quite a bit. So just be aware that that occurs. All right, with our understanding of statistical significance, we can actually proceed to the analysis. And there are two ways for us to do this. So the high accuracy method is when you compare a test statistic to your level of significance. Really, this is the way you should do it if you have time and the data and the relevant info to do it. This is definitely the preferred method. In this formula here on the top right, you will take the difference in means over the combined standard error, and this is going to produce your test statistic. If your test statistic is greater than your level of significance, then you can accept your alternative hypothesis. So the industry standard use case is your test statistic greater than 1.2. 1.2 is the level of significance for a one-tailed test at a 0.1 alpha, which is the standard for odds measurement in most cases throughout the industry. You can change that 1.2 based on the confidence level of your test, but this is what we will typically see in industry. So is your test statistic greater than 1.2? Now, sometimes when we're moving quickly, we just have the opportunity to maybe eyeball the stats. I also find this method to be easy to logically understand, so I really like to review it. You can simply compare the confidence intervals and the means of your experimental and your control populations. So you need a mean, you need a standard deviation, and you need some arithmetic, and then you can do this. So 1.2 is the number of standard deviations we care about when once again, 0.1 alpha and a one-tailed test. If the test mean and the control mean are greater than 1.2 of their standard deviations away from each other, then you have a statistically significant difference, which means you've rejected the null hypothesis, you've accepted the alternative, and you did it very quickly. You can eyeball this. Now, if they don't actually overlap, this actually doesn't continue to hold true. If you have overlap between those confidence intervals, you will need to go back to the test statistic method to determine if they are in fact statistically significant or not. If you just do this and you have overlapping confidence intervals, you will increase your rate of false negatives. But it's very, very handy and very fast for spotting positive results. So take a look at these two questions here on the bottom right. You have question 1, an experiment control, a mean and a standard deviation for each, and you also have question 2. Spend just a moment on this, do the mental math, and see if you can arrive at which one of these results is statistically significant. So for question 1, you can see that these means are a mile apart and their standard deviations are not huge. You can quickly do this math in your head and say that, yeah, these results are statistically significant. It's easy math to do. In question 2, these are pretty close. If you apply the math, you'll see that the confidence intervals are overlapping, they touch each other. This is something where you should really go back and do the test statistic to determine if they are in fact significant or not. But as you can see, it's a handy way to scan a set of results and pick out the positives, but not as handy for when your results are closer together, when they're tighter. All right, we've analyzed our results. We've rejected the null hypothesis. We've accepted the alternative. Cool. So what does this mean again? So statistically significant differences mean the difference is not random. And if you have a properly executed test, you have a randomized controlled trial, no bias, no contamination, then you can attribute the difference between the test and control group back to the treatment. In other words, you can say with confidence that the advertising caused the test population to buy more than they would have otherwise. And that's a very powerful thing. That is what advertisers are looking for. It's the goal of their media dollars. And we've now been able to prove it with statistics and with science. All right, now some of the warnings that come alongside this. Because unfortunately, experimental results are not proof, or at least they're not universal proof or truth. And in ads research, they tend to be ephemeral. So the results that we find don't linger long, and therefore repetition is key. So, a video ad, it worked. Let's run it again. Well, what has changed in that time period that may change the way that these results work for us? Did the buy one, get one sale end? Did the season change? Did people already buy the product and they only have need for the one? So just as a matter of good science, you need to have your results be repeatable. A sample of one is very suspect. So especially as we start to think through things like false positives and also false negatives, having a single experiment isn't going to be educational enough. And part of that is because ads don't repeat again in the exact same environment in which they were originally run. Sometimes the ad just isn't as funny the 11th time you see it. So you must always be testing, and this will give you the body of evidence that you need in order to be able to really commit to a tactic or strategy. If the video ads worked 42 out of the last 50 times we ran them, we can say we like video ads. You were able to establish that heuristic. All right, and in addition to this warning about the number of experiments you need to run, we do need to spend a moment to talk about bias. Bias, it's really the sleeper when it comes to experimentation. You never see it coming, but it can be there. So bias is when your exposed and your control population are not identical. So this could be in terms of age. This can be in terms of income or geographic distribution. These are some common ones and they're relatively easy to detect. The real scary ones are much trickier to detect and aren't really feasible to do so on a campaign by campaign basis. And so this could be your control randomly just has 5% more likely to have tried the product already. Is that common? No, not really. Can it happen? Absolutely. So the key here with bias is imbalance between the test and control. So if I run a survey and only men respond, that's fine. If I run a survey and only men respond in the test population, and I get a mix of men and women in the control population, well, now we have bias. So as the researcher, if you find bias, you must act. At the very least, you must note it. Maybe you engage with your data science team and you can build a cool model to help correct it, but it cannot be hidden, and it should only be disregarded when the data strongly warrants it. We have more on this in a later lecture on how to present results with integrity, but at the very least, you should caution temperance with results when bias is detected. And in some unfortunate cases, you may need to disregard the results entirely. All right, everyone, thank you very much. We'll wrap this all up we'll wrap up for the week in our next lecture. Thank you.